have memory locations, you have registers. Okay, so one side is memory, one side is processor. One side is Malaysia, one side is Singapore, right? And then you have some instructions. This is a snapshot. When you run the instruction, some things will change. So the first one, you have this situation. So many arguments or parameters. You have to recognize that part of it is operand 2, right? So this part here is operand 2. Because operand 2 can be either a constant or a register with optional shift. This is the longest flavor of operand 2. And then whatever this value works out to, you're going to edit the contents of R0. Okay? You're going to do something to the contents of R1. You're going to add it to that, and you're going to put the result in R3. So this thing is going to be overwritten. Okay? So just this is a simple question. How to do it? You know the value in R1. When you shift it, it's like multiplying by 2 to the power of the number that you shift. So this would be, you know that it is 30. And then multiply by 2 to the power of 4, because it is SL4. You end up with actually 300. If you don't believe, you can actually write it out. Oops, sorry. 30 is actually in, so it's 0011, right? So if you shift in everything, all bits shift 4 times, it will end up being 16 times bigger, and then you will end up, of course, when you shift, you will introduce 4 new zeros inside, and definitely you have that's why it's not surprising that when you shift left by 430, you end up with hexadecimal 300. And then this is the value in R1 that you add to it, you end up with the 308. And then this 308 is the one that goes into the destination register R3. So this is something that you must be able to do in a few minutes. Okay. Then the other one, LDR R3. Okay, so this one, you know it. What you do is take the value in R2 as the base register, add it to the offset. This is going to be 3004. That is your effective address. This is the value that you are interested in. That value goes into the destination register R3, and which is what you're saying here, effective address 3004. This value goes into R3, but don't forget that when you have a post-index, pre-index addressing, you also update the value in the base register, and which becomes 3004. Okay, so this value updates the base register. If you didn't have the exclamation mark, the same value goes into R3, but this thing doesn't change. Then you come back to here. The third one, push. Lots of stack, multiple word. In the case of push, is actually which direction? Going from processor to stack in memory, which is actually a store. So I'm actually going to push the value of R1 and R3 into here. So R1 and R3, as we know, has 30 and 1, 2, 3, 4. So it is going into the stack, which has the initial stack pointer is here. It actually gets decremented. The first value goes in, gets decremented again second value goes in. One of them is R1, one of them is R3. Which one is which? Simple rule to remember. Smallest number goes to the smaller address. This is R1, this is R3. And if you look here, R1 is 30, R3 is 1234, which is exactly what happens here. But don't forget that the stack pointer is also updated. So the stack pointer originally had this value, now it has a new value. Okay.
Sorry,
yeah.
Smaller content or smaller register number?
Smaller register number. Smaller register number. So R1 goes into this, R3 goes into the higher address. Yeah. And then okay, now this part 4 is, you will not be able to recognize this because this one has 2 registers here and it's something that is a more advanced mode called register offset that we are not covering this semester. So ignore this part 4. When you see square bracket with 2 registers inside as part of the load and store, it's something that you don't need to know about. If you look at the questions in the past couple of years, you shouldn't have this type of questions anymore. Okay, so that's the first one. Now then, let's look at another question. Hey, how come I don't have the question without? Okay, never mind. So never mind. This is actually another question. I will give you the year and all that later, but it doesn't really matter. Okay. 2011 12 SEM 2, right? Okay. Now, so this one, you don't even have to remember that what you saw just now, the test and the TEQ that does this. Okay, the definition is given to you in the question because we want you to apply. We don't want you to just memorize definition from the textbook. Okay, that's why I say you memorize everything in the slides, you may still fail. Okay, because we are not going to ask you to just play back everything from the slide. You must practice and know how to use it. So in this case, test R2 immediate A, TEQ R2 with immediate A. We know that test is an AND. We know that TEQ is an exclusive OR. Okay. So the easiest way to do this is draw rectangles, right? So R2 is going to contain different values at different times. It may be 0, it may be all F's, it may be A. However, you are going to act on this with another value that is always A. So A is 1, 0, 1, 0, and everything 0 in front of it. Okay. If you are doing test is an AND, if you are doing TEQ is an exclusive OR. The instruction itself is EOR, but this is the operation. So, like for example, I just cover some of this, right? If this thing is 0, right? And bear in mind that when you do this, even though the result is discarded, it's going to affect the N, Z, B, and C flags. So you have to try and work out what the result is. You know whether it's full of zeros or full of ones or whatever. If everything is all 0, then of course the Z flag will be set. If the most significant bit is a 1, then the N flag will be set because then it will be a negative number. So like in this case, obviously when you end these two, you're going to end up with all zeros here. And if you're going to be all zeros here, the Z will be set, and this one has no 1 there, this one is 0. So when I do exclusive OR, whose truth table when it's exactly the same, it is 0. When it is not the same, it is 1. Okay. So the same thing now, if I exclusive OR, I'm going to end up with some ones in the result. And some ones in the result, clearly it's not going to be all 0. And this thing is going to be 0, exclusive OR 0 is going to be 0 here. That's why it's n is equals to 0. So that covers the first case. Now the second case is a little bit more interesting. When everything here is all F, right? And everything there is 1. And you end it, you know that this thing doesn't change. You're going to end up with some 1s there. Clearly it's not 0. This thing is 0 here. End it with the 1 is going to be 0, so not negative. However, when you do exclusive OR, you're going to find that there are going to be firstly some 1s here, so it's again not 0. But you find that exclusive OR between a 1 and a 0 is going to end up with a 1. So this thing is going to be a 1, and therefore n is equals to 1. Okay? And then finally, another thing that's more interesting is when it's A, and it's exactly the same, 1, 0, 1, 0. When you exclusive OR with the DEQ, it's going to end up with everything 0, and therefore Z is equals to 1. Okay, for this case. However, when you're ending it exactly the same, you're going to end up with some 1s here, so Z is equals to 0. However, the 0 and the 0 in this case, or for the A case, is going to be 0 here, so therefore n is equals to 0. Okay. So this is just showing you that it is not impossible, it's very easy, you know your concepts, you keep your mind clear during the exam, you draw the rectangle, write down a few bit values, and you should be able to tackle it without any problem. Okay.
So for 0, if everything have to be, the whole bit have to be on.
Everything 0, then the Z side will be set. Okay. So remember, Z equals to 1 means everything 0. Okay.
So for negative have to be the most
The
significant.
first one, the most significant bit. Okay. Okay. So now we come to the part that we're going to try and write some programs. Okay. Now this is a typical question. So for example, you will be normally given some simple thing to compute, either some mean or some variance or some simple formula. Okay. So like in this case, you try to unpack the question and read it carefully. Okay. So you're going to compute the approximate mean x bar and variance s squared. So the formula is given to you. Okay. Of a list of numbers. Okay. If you try to draw pictures, right? So in memory, you have a list of numbers. Xi, where I goes 1 to n, and they are stored in memory starting in location numbers. So, draw some boxes. Okay. And numbers is a label. You don't really need to know what it is, but it is a label. And there are some values inside. So let's say we have 6 values. So maybe some value here 100, 25, 7, 6, 3, 1, 2, 3, for example. Okay. So these are some numbers inside memory, and then there's the value of n, which is how many numbers you have, is stored in here. So you have 6 numbers. Okay. And you want to find the average of this list of numbers. So mean is average, right? And as we know, calculate average is go here, get the number, add it, the total, you're going to divide by 6. So very easy. Now the thing is, when you want to write a program, at the first part of the program, what do you normally write? You need to initialize some registers or some values, usually, right? So, standard, the first part of the program is initialize. And initialize normally involves loading some values, either using PC relative addressing or pseudo instruction, equal sign, kind of thing. Usually will involve that. Then the next thing that you want to bear in mind is you ask yourself whether there is a loop. Okay? So do you think in this question we need to have a loop?
Yes.
Because we are going to process a list of numbers, right? So we will have a loop. Do you think we need to use load to load some of these values? We need to load some of these values into the processor registers, right? In order to work on them. So load is definitely required. Okay. Now the thing is, this is summation, so you will expect add to be required. After that, you need to divide. You know that divide is going to be required. But because these numbers actually some of them can be negative also, you need to do a sign divide. Okay. So you expect your program to have all these things. Now the thing is, the question also says when you compute the mean and variance, you will store them at consecutive memory locations starting from location answer. So there are also additional memory locations answer. What you want to do is you want to store the mean here, and then in the next one you want to store the S squared value, the variance here. So now we have probably some idea how to compute the mean. But if you look at how to compute the variance, it looks like we need to loop one more time, right? Because when we compute the variance, we have to use this mean value here. We take the raw value, subtract the mean, and then we have to multiply by itself to square it. And then we need to add it together. Now, do you know of an instruction that can multiply as well as accumulate or add numbers? Which is multiply or accumulate, right? So we will be using multiply with accumulate, okay, to do this. And then we also have to divide and so on. So you know that once you have a loop also, you're going to have a loop counter. You're going to subtract the loop counter every time you go around. And when it hits 0, you're going to jump out of the loop. So the branch, whether BGT or BME, is going to be there. So you can't run away from all this. So the code, although it has many lines, but the loop 1 and loop 2 are fairly similar. Later on, we'll look at another example where the program is actually shorter, but that's because you don't need to repeat some things. So the first part here is the initialization part that I mentioned. Okay, always start your program with initialization. You need to get the number, the n. Okay, this number 6. You need to know that you are going to load values, 6 values. Okay, so you're going to loop around 6 times. You need to know where to get the numbers from. So you need this address, you need this address. You need the address, which is the value of the label. You need to use the pseudo instruction with the equal sign. So this is equal numbers. The n has no equal sign because we're getting the value 6 itself. The answer is the address itself. Okay. So this is done. Then after that, the first loop is here. This one, if you do post-index addressing, is useful, right? if you do post-index addressing, is useful. Now, all you take photo, please don't put on Facebook or YouTube or whatever, okay? It's only for your own consumption. So the thing is, here, you are going to load these values one by one, okay? So you know the address is inside R1, you put it as the base register, you load it one after another. Every time you get it, you are going to accumulate it, and then finally the sum is in R4, right? This loop is standard. You actually decrement the loop index until it hits 0, then you stop. But then the thing is, you need to divide it. So since you have already made this one 0, you need to load it one more time. Otherwise, you're going to divide with 0, right? So you divide the sum with the number, and after that, you store it in the first thing here. You store the first result, the mean. Then after that, you get ready to do the variance part. You actually need to also go and get these numbers again, because when you are using the base register in the post-index addressing, this thing gets incremented. So at the end of the day, it was actually pointing to here. You actually want it to point back here to fetch this value again to do this one. So you set this R0 and R1, get the values again, but this time you subtract the R5, which is actually storing the, this is the X bar value, right? You subtract it, you get it in R6, and then you square it here, and then you accumulate with R4. And then at the end of the day, when you finish this loop, you again need to divide by n minus 1. So you need to load it again because it has already been decremented to 0. You minus 1, because it's n minus 1, divide it, final answer here. R3 contains R3 contains this address now. So you just store it there because this R3 was already implemented earlier on. You store it inside here, and that's it. Don't need to worry about this. It's assumed to be done. So this is it, okay? Now, if you first time look at it, of course, you cannot do it in half an hour. But with some practice, and if you know that it is usually this kind of format and style, you should be able to do it within half an hour. Okay. Let's look at another example, which is this slightly different question. Okay, so this was the question from just now, right? Slightly different question. Again, some simple formula, convert Fahrenheit to centigrade. Okay. Read the question carefully. Do not miss out important words. It says with a subroutine. Okay. So with subroutine, you know you have BL. You know you have BXLR. You leave out, you're going to lose quite a lot of marks. So don't quickly jump into the question. Read carefully. Again, it is possible to have positive and negative temperature values. You have a list of n temperature values, so very similar. You have picture in memory. You have picture in memory. Okay, let me just draw it here. You are going to take a number here. This one is the Fahrenheit value. Let's say first value F1, second value F2. Okay. You're going to take the first value, and the list has a label. This one is in-val or input value. You're going to take it, you're going to call a subroutine and convert it to centigrade. You're going to put it in a new list called out-val. Okay, so this is C1. F1 becomes C1. F2 becomes C2. First Fahrenheit value becomes first centigrade value. Second Fahrenheit value becomes second centigrade value. Okay. And then there's an n that tells you how many numbers there are. Okay. So the thing is, your original Fahrenheit temperature may have 2 decimal places, but we know that we don't cover processing of floating point numbers in assembly language. So it has been converted to integers. So let's say you have a temperature like 50.23. Okay. So you will convert it such that the value that's actually stored there is an integer that is like 5023. Okay. So 5023 is like you actually have a data conversion operation before you ran the assembly language. So the part B asks you what do you do. So this one is like you multiply by 100, right? Now if you multiply by 100, you cannot just minus 32. It doesn't make sense. You must minus similarly scaled value. So this one later you must convert it to 3200. So it's going to be 5023 minus 3200. This times 5 over 9, no problem, because no need to do anything. This cancels off. Okay. Apply the same considerations. You need to do some initialization. LDR, you're going to load some labels. You're going to then you ask yourself a question. So initialization sure must do. Loop. Any loops? List of values sure must have loop. If you have loop, you have a loop counter, you have a subtraction of loop counter, you have a BNE or BGT usually, and then those standard features. So code is not very long. It looks a bit like this. So this is the initialization part. Usually involves some PC relative addressing and also some pseudo instruction load to get it into some registers that you can work with. Then after that, I also need to get additional things ready. Because I'm going to subtract 3200, so I get ready. I'm also going to, now actually this 3200, I can subtract an immediate, so it's not so important to move it into a register. However, the 5 and the 9 is going to involve multiply and divide. And if you remember the format for multiply and divide, you cannot specify immediate or multiply and divide. It has to be in a register. So that's why I have to put the 5 and 9 in registers, even though they are small values. Okay. For example, just to emphasize what I'm saying, I cannot say multiply R0, R1, hash 5. There's no such thing. Okay. I must put this 5 in the register and say multiply R0, R1, R2. I must put that 5 inside R2 to do it. So which is basically what I'm doing here. Okay. Same thing goes for divide. I cannot just have an immediate for divide. So coming to this, the main part of the program, my loop actually goes through that list just now. But the logic is actually very easy. I take the first value, I call a subroutine, it converts it to centigrade, I save it to the list starting from out down. So to do that, I load the first value, call the subroutine. The answer is actually in R4. I save it into the second list. So essentially, it's like what I said. Take this one, call subroutine, convert the centigrade, put in answer in R4, write the R4 value here. Next one, take this one, load it, call the subroutine, answer in R4, write it here, and so on until you finish the loop, which is what we are doing here. Decrement the loop counter, and that's it. And then inside the subroutine itself, And when you call the subroutine, of course, it's a DL. But inside the subroutine itself is where you are doing that minus 3200. So here I could have written 3200 as immediate, or I could have put the 3200 into R5 and call it like this. Then I will multiply by 5, divide by 9, VXLR, okay, to return to this line straight away, store it. I don't need this, it's still to be all set up. And so actually, wow, very easy. 15 to 20 marks just to write like 7, 8 lines, very easy. Okay. Half an hour, lots of time. Okay. Yeah. So can do, right? All of you can do. Okay, I did tell you that I will stop at 7:30. So before we all go, I will just quickly show you one other question that uses the bit clear thing. This is related to the pin connect block and the pin function selection, right? If you want to select certain functions, and also to emphasize that you don't need to memorize anything. Table information all given to you. You just need to know how to read the table. I want to choose this functionality. Therefore, I'm going to set certain bits to 0, 1. Okay. So which bits are these? 20 to 27. So all I need to do is to count until bit 20, 27, one whole bunch of 8 bits, right? 2, 4, 6, 8. 1, 2, 3, 4, 5, 6, 7, 8. This 8 bits, I want to change it. Change it to what? Change it to 0, 1, 0, 1, 0, 1, 0, 1 to select these functions. Right? So 0, 1, 0, 1, 0, 1, 0, 1. The rest, don't touch, don't change. Only affect this part. Now, because it is 0, 1, I cannot just OR it in the pattern, or I cannot end it in the pattern. We covered this in tutorial. You need to clear it first. And to clear it, use what instruction? Bit clear. Okay. So bit clear, you specify a pattern that I want to clear this 8 bits. So it's going to be 8 ones there. And then the rest all 0. And then 4 zeros in front. And I'm going to bit clear some register with this pattern that is also in another register. But of course, I don't write it all in binary. I write it in hexadecimal. So it will look something like this. Okay. So this is the one that I want. To do this, first of all, recognize in hexadecimal actually it is 0, 5, 5, and then the rest is actually all A's, okay, which is the score that all you are going to get, right, for this module. The grade that all of you are going to get. Okay. Then, if you were to write assembly language instruction, you assume that this address is actually already in R0. Load it first into R1, so the original pattern goes into R1. You bit clear those 8 bits by specifying this hexadecimal pattern. Okay, so it's going to have the effect of clearing all this to 0. Then after that, you will OR with 5, 5. Okay, and then the answer you store it back into the pin cell register, and then it is done. Okay. So this is you have seen this before in the tutorial sheet, but I just wanted to refresh your memory about this. Okay. So actually, that's all I want to talk about today. Like I said at the beginning, it is just guide you a little bit in your revision and also to show you a little bit about the type of questions that you're likely to encounter. And to also emphasize that please don't memorize, but know how to apply. Work out some of these problems, discuss with your friends, and I'm confident that most of you will do well. Okay? If you have studied hard way the effort, you should be able to do well. It's a very close relationship between the assignments and the lecture and tutorial material. Okay? And I think you still have to do your assignment assessments, so get on with it and see you at the exam hall. Okay? 23rd. Alright? Okay, good night.
Two of your tutors will be conducting a revision session following this at the respective tutorial rooms, Dr. Locke and Christopher. Sakit had conducted some level of revision in the last week, so he will be conducting it. So you can go to either of the two tutorial rooms if you belong to the respective tutorial.